Welcome back. Today we are going to explore something called polar coordinates. So we're going to be polar explorers. Anyways, yeah, I need help. Okay, we're going to look at polar coordinates. We're going to see what they are, how they work, how to graph with them, etc. And then in the near future, we'll also explore graphs of polar equations. And that's a lot of fun. Those graphs look really cool. Okay, now so far we have worked with rectangular coordinates. Rectangular coordinates, you had an x, y, like let's say you had 4, 4. That was an x, y. So you looked at, you had an x-axis and a y-axis. 4, 4, you would go right 4, up 4, and plot a point. And that was based on an x-axis and a y-axis. But now with polar coordinates, the pairs are going to be in the form of r theta. Okay, the polar coordinates, they're based on a point called the pole, and then a ray called the polar axis. And I'm going to go ahead and situate this pole at the origin. On top of I'm going to superimpose the pole on top of the origin of the xy coordinates and the polar axis on the positive x-axis. And with this system, what we do is we look at these points, and instead of having xy coordinates, what we have is r, theta. We explore, well, how far from the pole is it? That's our r. And what's the theta? So in this case, r, theta, we're looking, the r, we got to think about right triangles here. You have 4 and 4. R is square root of 4 squared plus 4 squared. So square root of 32, or 4 square roots of 2, right? Because 16 plus 16 is 32. You know, or 2 times 16, square root of 16 is 4, 2. All right. So the polar coordinates would be 4 square roots of 2, comma, and then this theta is 45 degrees. You could either have it in degrees or in radians. So you could go ahead and say 45 degrees if you want, or you could say pi over 4 for the radians if you want. So it's based on, you've got the pole, you've got the polar axis, and then from the polar axis you're looking at, okay, what's the distance of that point from the pole, and what's the theta, the angle from the polar axis. Now usually when we, okay, and a couple little notes, you know, when we're doing this, if we look at theta in the counterclockwise direction, that's going to be a positive theta. And if we look at it in the clockwise direction, that's going to be a negative theta, just like we've worked with before. And usually these polar coordinates are graphed on a polar grid. So here's a nice little polar grid for you. Notice the circular nature of it. When you're looking at the polar grid, it almost looks like you see the xy axis system in there. 0 degrees and pi looks, you know, it looks like you have the x-axis there, and then 90 degrees and 270 degrees here. It looks like you have the y-axis. But if you're going to graph something like 4 square roots of 2, 45 degrees on the polar grid, what you do is you look at the angle. You start from 0 degrees, right here. You start from the polar axis. The pole's here in the middle. Here's the polar axis. You start from there and you find your angle. In this case, positive 45 degrees. There it is. And then 4 square roots of 2. Let me put that in a calculator just to get a rough decimal for that. oops, excuse me, I meant to hit the parenthesis. You get around 5.6766. So around 5.66, 45 degrees. So at the 45 degrees, from the pole, you count out, each circle is a unit. So you count out 1, 2, 3, 4, 5. 5.66 is just a little past 5.5, and you put a dot there. And that dot represents 4 square roots of 2, 45 degrees in the polar coordinates. All right, let's look at a couple more. Let's do 3, 315 degrees. I'll do them in different colors so you can see each one. Well, find 350, starting from the polar axis, go to 315 degrees. So you go around, here's the 315 degree mark. And 3 means you're going to count from the pole 1, 2, 3. So you end up right there. So there's your 3, 315 degrees. Now if you have something like -2, pi, you start from the polar axis, go to pi, so go to your angle first. But a -2 means instead of counting 1, 2 along pi, go the opposite direction, 1, 2. Complete opposite direction. And that's how you'll get -2, pi. So even though this dot is on the 0 degree mark, it's there because of this -2. And -2 is telling us go backwards, go opposite direction from pi, and go 2 units. Alright, let's do -1, pi over 2. Alright, tackle the angle first. So going around, -pi over 2 is going to actually get you to here. Because negative, you're going in the clockwise direction. -pi over 2 is going to get you here. If it had been 1, pi over 2, you'd mark at the 1. But it's -1, so that's going to put you here. -1, pi over 2. There's that. So that shows you, it gives you some exposure to what happens also with negatives on the polar coordinate axis here. Now let's do one more, and then we're going to take that one and explore it a little bit. Let's take 5, pi over 4 and do it next. Let's see, I'm going to use red this time. Alright, I'm going to start from the polar axis. I'm going to go to pi over 4, and I'm going to go out 1, 2, 3, 4, 5. That puts me right here. But I'm interested in seeing what other ways I can express that. What other coordinates can I use for that same exact point? I'm using 5, pi over 4 right now, but how else could I express that same exact location? Well, we went positive pi over 4 and went out positive 5. You know what we could have done instead is we could have gone the opposite direction around, and we could have gone negative 7 pi over 4, right? And still be 5 out. You guys see what happened there? Starting from the polar axis, go around negative 7 pi over 4, and then count out 1, 2, 3, 4, 5. Or, what if we wanted to use -5 as our coordinate? Well, we would need to be along this line here. If we were at 5 pi over 4, so if we went around to 5 pi over 4 right here, and went -5, we'd have to go the opposite direction, and end up here. So that's another way to express the same location. Or you could do -5 comma, maybe instead of using 5 pi over 4, go this direction, -3 pi over 4. So there's all kinds of possibilities. You know, if you went -3 pi over 4, you'd end up here, and then went -5, opposite direction, you end up there. All sorts of possibilities. So those are just a few of several ways you could express the same location. So be aware that with polar coordinates, there's not always one way to write the coordinates, especially since you're dealing with angles. And since a -r means you go opposite direction, there's all kinds of things you could end up doing here. Okay, so that's an introduction to how to graph with the polar coordinates and so forth. Now, the interesting thing is that you can actually convert back and forth between polar and rectangular coordinates. If you think about it, it makes sense that you're able to convert. Because back in the original example, I had the point 4, 4 in the xy system, in the rectangular system, but you can convert that to polar by looking at what the theta is and what the r is. And that's exactly what we're going to be doing here. Okay, let's say you have a point out here, x, y. Okay, so right now we're looking at it as rectangular coordinates. And here we got these oldies but goodies. You know, this dimension here is x, this dimension here is y. We can go ahead and label this one r. And then we also have our angle theta. Right here you got 0, 0. According to the Pythagorean theorem, x squared plus y squared equals r squared. X squared plus y squared equals r squared. And that's important when we're trying to convert. If we know x and y, we can convert to r. Also, if we know r and theta, if we look at this closely, we know that the cosine of theta is x over r. So that tells us that x equals r times cosine theta. So that's important. Sine of theta equals y over r. So let's do a quick little algebra. Y equals r sine theta. Circle that. Tangent of theta equals y over x. That's also important to know. You can use all of these to convert back and forth from polar to rectangular and from rectangular to polar coordinates. All right. Let's start with 3, pi. These are in polar. And let's see about converting them to rectangular. The r is 3, theta is pi. Well, if x equals r cosine theta, then x equals 3 times cosine of pi. So that's 3 times -1 or -3. And if y equals r sine theta, then y equals 3 times sine of pi. So that's 3 times 0 or 0. So the rectangular coordinates for that same point would be negative 3, 0. Okay, what if you were given the rectangular coordinates? What if you were given 1 comma negative square root of 3? You wanted to convert that to polar. Well, r equals the square root of x squared plus y squared. So r equals the square root of 1 squared plus negative square root of 3 squared. So r is the square root of 1 plus 3, which is the square root of 4, or 2. Then tangent of theta equals y over x. So theta is the inverse tangent of y over x. So in this case, the inverse tangent of negative square root of 3 over 1, or negative square root of 3. If you think about this, our original point, 1 square root of negative 3, is going to be over here somewhere in quadrant 4, right? So if you look in quadrant 4, the inverse tangent of negative square root of 3 is going to give you 5 pi over 3. So the rectangular coordinates are 1 comma square root of negative 3. The polar coordinates are 2 comma 5 pi over 3. They both describe the same location. It's just different systems. One's in the xy axis system, the other is in the r theta system. Just like you can convert coordinates back and forth, you can also take equations and go back and forth. Okay, how about we go from rectangular to polar first? Let's say you have the linear equation, 3x minus y equals 6. And you want to convert that to polar. Well, you know x is really r cosine theta. And you know y is really r sine theta. So you got, factor out the r. You got 3 cosine theta minus sine theta. And that equals 6. So r equals 6 over 3 cosine theta minus sine theta. Okay, interesting. You've actually got the polar equation of the same line. Like if you take 3x minus y equals 6 and you graph it right now. Let's see, it has a y-intercept at negative 6. Has a slope of 3. 1, 2, 3. 1, 2, 3, 1. 1, 2, 3, 1. And it looks roughly like this. But let's put this in the calculator and graph it in polar form. Let's go to mode. And let's go down to where it says func for function, and we want to go to polar mode. So let's select polar, POL. You know, function, parametric, polar. So then now when you go to y equals, instead of y1 you have r1. Well, r1 equals 6 divided by, I'm going to put in parentheses, 3 cosine. And when you hit the xt theta in button, it's going to put theta there because you're in polar form. Minus sine theta. And then let's hit graph. And I'm going to go ahead and, let's see, I'm going to zoom. I'm going to do number 5, z squared. No, that's probably not enough. How about z standard number 6? That'll take you negative 10 to 10. Alright, there's your line. It has a y-intercept at 0, negative 6, and then it has an x-intercept at 2, 0. But guess what? I didn't graph that line using 3x minus y equals 6. I graphed it using the polar form of the equation. Same line, just two different forms for the two different equation forms to describe the same line. Pretty cool, huh? All right, let's do another one. This one's actually a circle. X squared plus y plus 1 squared equals 1. So whereas we had a line here, this one's going to be a circle. The center is at 0, negative 1, and the radius is 1. Let's put it in polar form. Let's replace x with r cosine theta, and let's replace y with r sine theta. So we got r squared cosine squared theta plus then r squared sine squared theta plus 2r sine theta plus 1 equals 1. Factor r squared out of these two. And I'm doing that because I recognize cosine squared plus sine squared. One of my classic identities there. Cosine squared plus sine squared is just 1. So I've got r squared plus 2r sine theta. And I can subtract 1 from both sides and set that equal to 0. So I got r times r plus 2 sine theta equals 0. So you got r equals 0, and r plus 2 sine theta equals 0. R equals negative 2 sine theta. Well, when theta is 0, negative 2 sine theta equals 0. So we don't need to include this one, because it's r equals 0 is built into here when theta is 0. So we can just use that one, save us some time and energy. But check this out. Again, I'm still in polar form, and I'm going to go back to this menu, and I'm going to type in negative 2 sine theta. Oops, why did I put the sign in there? Negative 2 sine theta. Dang it. Keep hitting those wrong buttons. Alright. Oh, I don't like that one. Let's see here. Zoom in. Number 2. Enter. There's my circle. The center is at 0, negative 1 right here. The radius is 1 unit all the way around. Doesn't look very circular. That's because when I zoomed before I had done z standard. Let's do z square. Let's square it up. And it'll look a little more circular. But it is a graphing calculator, so it has pixel limitations. So the circle looks a little flat on the sides here, but you should be aware it is a circle based on the equations. Okay? And just like we can go rectangular to polar, we can also go polar to rectangular too. There's no stopping us. First example, if you have r equals 4, that's in polar. Well, we know r squared equals x squared plus y squared. So let's see if we square both sides. R squared equals 16. So x squared plus y squared equals 16. That's a circle with center at 0, 0, radius of 4. This one you should recognize from algebra. Circle with center at 0 at the origin, radius of square root of 16 or 4. Well, if you go back here and just type in 4 and hit graph, ooh, zoom out a little bit. There's your circle, centered at 0, 0 with a radius of 4. Voila. If you have theta equals 3 pi over 4. Oh, by the way, yeah, think about this. R equals 4. Basically, it's saying you're including every possible theta, but the distance always has to be 4 from the pole. Whereas this one, your theta has to be 3 pi over 4, but you're including every possible r. So this is kind of an interesting thing. Let's see here. Let's take the tangent of theta. Let's take tangent of 3 pi over 4. And we get -1. Well, tangent of theta is the same thing as y over x. And in this case, y over x equals -1, so y equals -x. All right, that's a line with, goes through the origin, slope of -1. Think about it. 3 pi over 4 is going to put you here. And if you're including every possible r, that means every possible distance from the origin, you're going to be like this, which is the same as the line y equals -x. All right, let's say you have something like r equals -2 secant theta. Well, there's those lovely secants, you know, which we know secant is the same thing as 1 over cosine. So let's see, r cosine theta equals -2. Well, that's convenient. R cosine theta is the same thing as x. X equals -2. That's a vertical line. X equals -2 is. Let's see here. Let's put it in to y equals. Let's put -2 divided by cosine theta. There's your vertical line. X equals -2. Or last but not least, let's do r equals 10 sine theta. Hmm. 10 sine theta. I'm trying to convert somehow to x's and y's. I've got an r and a theta here. Let's see, previous strategies, like up here, r equals 4. I have squared both sides to get an r squared. But you know what, if I square both sides here, I'm going to get r squared equals 100 sine squared theta. And I'm not going to know what to do with that sine squared theta when I'm trying to convert to x's and y's. I could take the r squared and turn it into x squared plus y squared, but what do I do with sine squared theta? You know, different strategy. What if I multiply both sides by r so that I get my r squared, but watch this. I've got an r sine theta. And I know r sine theta to be same thing as y. And then the r squared, of course, is x squared plus y squared. So x squared plus y squared minus 10y equals 0. This is actually a circle. Complete the square, and you'll get your circle equation. X squared will be just x minus 0 squared. But here, half of 10 is 5. Square that, you get 25. So if you add 25 to both, this turns into y minus 5 squared. And all this equals 25. That's what completing the square thing when you're dealing with circle equations. So you have a circle with a center at 0, 5. And then the radius is the square root of 25, or 5. Let's do the polar form. 10 sine theta graph. And there it is. The center is at 0, 5 right here, and the radius is 5 all around. Oops, let's try. So whether it's in polar or rectangular, it's the same figure. Okay, well that's your introduction to polar coordinates. A little bit about graphing them, a little bit about how you can express them, how you can convert between the rectangular and polar coordinates, and how you can convert between rectangular and polar equations. Next up will be to take some very interesting polar equations and graph them. They don't always come out to be lines or circles. Sometimes they come out to be some other really fun stuff like limaçons and limnoscates and things like that, and some pretty flowers. So that's where you're going to tune in next time and join us to learn about that, about the graphing. Thank you very much.